Hello everyone. Let us continue our discussion on Fourier series representation of a rectangular wave. So let us consider a rectangular wave that is on from some minus t1 to plus t1 and has a period of t0. So this is t0. Let this be xt. We want to find the Fourier series representation of this wave, and let us first start with the complex exponential Fourier series representation. So I have redrawn this rectangular wave here, where the amplitude when the wave is not zero is a. So during minus t1 to t1, the amplitude is a, and the period of this waveform is t0. So if I want to represent xt as a summation of complex exponentials, C0, which is the average of this waveform over an interval t0, would be 1 upon t0. Now, since this is a symmetric wave, a convenient interval to consider over one period can be minus t0 by 2 to plus t0 by 2. In this interval minus t0 by 2 to plus t0 by 2, this waveform is equal to a, which is a non-zero value only between minus t1 and plus t1. That changes my limits from minus t1 to plus t1 a dt. This would give me 2t1 by t0 into a. This is the value of the 0th coefficient. Now finding ck for k not equal to 0. That ck is 1 upon t0 integration from minus t0 by 2 to plus t0 by 2 xt e to the power minus j k omega naught t dt. I can simply change these limits to minus t1 to plus t1 and say that xt in this interval is a. This is equal to a upon minus j k omega naught t0, and the integration of this term is e to the power minus j k omega naught t, limits from minus t1 to plus t1. This is equal to a upon minus j k. Now omega naught t0 is 2 pi, and when I plug in these limits t1 to minus t1, this becomes e to the power minus j k omega naught t1 minus e to the power j k omega naught t1. I can rewrite this term as a upon k pi e to the power j k omega naught t1, this term, minus, so I'm just multiplying numerator and denominator with minus 1, e to the power minus j k omega naught t1 upon 2j. Now this term is equal to sine k omega naught t1, right? So I can simply write that this is equal to a upon k pi sine k omega naught t1. So when k is equal to 0, this is equal to a into 2t1 by t0. ck is equal to a upon k pi sine k omega naught t1 when k is not equal to 0. Rewrite omega naught as 2 pi by t0. So this becomes a sine k 2 pi by t0 t1 upon k pi, which is equal to a sine k pi into 2t1 upon t0 upon k pi. Now remember that a sinc function, sinc of x, is represented as sine pi x by pi x. That means if I wanted to represent this as sinc of some argument. The argument that I have is this. Okay, so I need to bring it as sine pi into something upon pi something. So the only thing missing here is 2t1 by t naught. If I multiply and divide by 2t1 by t naught, this becomes 2t1 by t naught into a sine pi into k 2t1 by t naught upon pi 2t1 by t naught, and I can simply write this as 2t1 by t naught a sinc of k 2t1 by t naught. Why is this important, or how is this sinc function relevant? We'll see in a short while. So we found that for that rectangular wave, C naught is 2t1 by t naught into a, and ck is equal to a into sine k pi 2t1 by t naught upon k pi. Now let us, this is for when k is not equal to 0. K can take integral values. So let us see what these values are, what these coefficients are, if say, if t naught is equal to 4t1, that means it is a square wave. The case like this. That means the total duration of on time is same as off time. So this is t naught by 4. This is minus t naught by 4. So t1 is basically t naught by 4. Okay. So this implies that 2t1 by t naught is actually 1 by 2. In that case, c naught becomes a by 2 and ck becomes a upon k pi sine k pi by 2. Now this term sine k pi by 2, this is equal to what? This is equal to 0 when k is equal to, this is equal to 1 when k is equal to 1, it's equal to 0 when k is equal to 2. When k is equal to 3, this is sine 3 pi by 2, so this is minus 1. When k is equal to 4, this is equal to 0 again. When k is equal to 5, this is equal to 1 again, and so on. That means for all the even values of k, this value comes out to be 0, and for all the odd values, sine k pi by 2 is not 0, but it oscillates alternately between 1 and minus 1. So I could simply say that I could rewrite this as that sine k pi by 2 is equal to 0 when k is even. That means k is equal to some 2m, if m is also an integer. When k is equal to 2m, that means when k is even, sine k pi by 2 is 0, and when k is some odd number, for example k is some 2m plus 1, in that case this value is actually minus 1 to the power m, meaning when k is equal to 1, that means m is equal to 0. That time we found that sine k pi by 2 was equal to 1. When m is equal to 1, m equal to 1, that means k equal to 3, we found that this term is equal to, was equal to minus 1. So minus 1 to the power 1, minus 1. For k equal to 5, that means m is equal to 2. That time sine k pi by 2 will come out to be 1 again. So I can rewrite the value of sine k pi by 2 as minus 1 to the power m when k is odd, that means k is some 2m plus 1. And it is 0 when k is even, that means k is some 2m. That means I can rewrite the value of ck. This would be equal to 0 for k is equal to 2m but not equal to 0. That means an even value of k. And this would be equal to a into minus 1 to the power m upon k pi for k is equal to 2m plus 1. Since my notation has now gone in terms of m, that means I'll now take all values of m. I can rewrite this again in terms of m and say that c of 2m is equal to 0 and c of 2m plus 1 is actually equal to minus 1 to the power m a upon 2m plus 1 pi. This would ensure that when I write a summation, I actually consider all values of m and not just selective values of k. That is why I have done this change in variable. So how can I write the complex exponential Fourier series representation of xt now? Xt is equal to ck e to the power j k omega naught t, where k would vary from minus infinity to infinity. If I just look at c0 where k is equal to 0, I have that value as a by 2. All the even values of k, that means k of the form 2m, they are all 0. That means they do not feature in my summation anymore. What features is all the odd values of k, but I cannot write a summation in terms of k by specifying odd values of k. So I need a change of variable so that summation includes all possible values of the integer. So I can write this as c0 is a by 2 plus, note that I am trying to rewrite this term, a upon k pi minus 1 to the power m. That means instead of k also I will have 2m plus 1 pi. This is the term. So this becomes a by pi is a constant outside, summation of minus 1 to the power m upon 2m plus 1 and all the odd harmonics, right? Because k is only 2m plus 1. So e to the power j, where used to be k, now it will be 2m plus 1 omega naught t. Now m varies from minus infinity to plus infinity. This summation does not involve the c0 term. The c0 term has come in here and these are all the remaining terms. So I can say that xt, which was a square wave like this, it became a square wave because now the on time was equal to off time. We initially started it with some general value t1 and later we substituted t0 by 4. So then it became a square wave. If this is xt, this is its Fourier series representation in terms of complex exponentials. Now, as mentioned earlier, a sinc function is defined as sine pi x by pi x, and its name comes from the word sine cardinal, popularly called as sine c or sinc. What effectively it means is this is a sine wave whose amplitude decays by 1 by x. It's a waveform that looks like this. It has a gradually decaying amplitude. Its amplitude at x equal to 0 is 1 and gradually decreases by a factor of 1 by x. We've already shown that for this first example, all the even coefficients come out to be 0, m not equal to 0. All the odd coefficients are basically minus 1 to the power m, 1 upon 2m plus 1 pi, and c0 is 1 by 2 if a is equal to 1. So if I draw the Fourier spectrum, that means in terms of k, and I try to plot ck. For k equal to 0, ck is equal to 1 by 2. For all the even values, coefficients ck are 0. For k equal to 1, C1 is equal to C of minus 1, which is 1 by pi. Similarly, C of 3 is equal to C of minus 3, which is minus 1 upon 3 pi. Similarly, C of 5 is C of minus 5, which is equal to 1 upon 5 pi. And all even coefficients are 0. And the 0th coefficient is 1 by 2. So this is some 1 by pi. Then 1 upon 3 pi in the negative direction. Then 1 upon 5 pi. Similarly 1 upon 7 pi. This is called the Fourier spectrum. The envelope of which follows a sinc function. Let us continue our discussion. Now, how about writing the trigonometric Fourier series representation? Trigonometric Fourier series representation is of the form xt is equal to a naught plus summation ak cos k omega naught t, where k varies from 1 to infinity, plus summation bk sin k omega naught t, k varying from 1 to infinity. In an earlier lecture, we have already found a relationship between complex exponential Fourier coefficients and trigonometric Fourier coefficients. And we said that if we know the complex exponential Fourier coefficients, trigonometric Fourier coefficients can be found as a0 is simply c0, ak is twice the real part of ck, and bk is minus 2 the imaginary part of ck. Now we found that ck in complex exponential representation was actually a real number, so it does not have an imaginary part. That means bk in our current case would be equal to 0 because ck does not have an imaginary part. It's only real, because ck was found to be what? ck was found to be c some 2m plus 1, which was actually equal to a into minus 1 to the power m upon 2m plus 1 pi. Does not have any imaginary component. This is for k not equal to 0. It was also kind of obvious because this xt is an even function. We could directly say that its Fourier series representation would not have any sine terms, it would have only cos terms. a0 now is simply c0, that is a by 2. ak for even k, that means a2m, is twice the real part of c2m. It's twice the real part of even k, which is equal to 0, because all the even k's came out to be 0, if you remember. ak for odd k means a of the form a2m plus 1. This would be equal to 2 real part of c2m plus 1, meaning real part of all the odd ck's. This would be equal to 2 into the real part of odd k's, that is equal to minus 1 to the power m a upon 2m plus 1 pi, and all the bk's are 0. So I can rewrite this trigonometric Fourier series representation as xt is equal to a by 2 plus 2a by pi summation minus 1 to the power m upon 2m plus 1. Now only the odd cos terms would feature. Sine terms were anyway not going to feature because all bk's came out to be 0. Even among the cos terms, all the even cos terms are 0. Only odd cos terms occur. So odd cos terms means cos 2m plus 1 of the form cos 2m plus 1 omega naught t. This is what features. Now m varies from minus infinity to plus infinity. A by 2 plus 2a by pi. Now I can simply just find the first few terms. So when m is equal to 0, this is equal to 1 upon 1 cos omega naught t. Cos omega naught t. When m is equal to 1, denominator is 3 and numerator is minus 1 because minus 1 to the power 1. So this is minus 1 by 3 cos 3 omega naught t. Okay. Then when m is equal to 2, denominator is 5 and numerator is again minus 1 to the power 2, that means 1. So 1 upon 5 cos 5 omega naught t, and so on. So this is now the trigonometric Fourier series representation of xt. And because xt was even, you can see that there are no sine terms, and we also found that there are only cos terms, but even the even harmonics of cos terms have no component here. Let us consider another waveform. This would also be a square wave, but just slightly different from the earlier one. This is a wave like this. So this is 0. This is A. This is T naught. This is T naught by 2. This is minus T naught. This is minus T naught by 2. And so on. So this is basically just like the earlier wave that we looked at, that we saw, but shifted towards the right by an amount T naught by 2. So let us find the complex exponential and trigonometric Fourier series representation of this wave now. Starting with complex exponential. C0 is the average value over a period. Now everything in a period is same in this waveform as it was earlier. So C naught will still come out to be A naught by 2. Now for k not equal to 0, I can say that Ck is equal to 1 upon T naught. Integration, now I can take, it's more convenient now because this is an odd function, it's more convenient to take the period from 0 to T naught. So 0 to T naught xt e to the power minus j k omega naught t dt. This would be equal to 1 upon T naught. This is equal to non-zero value only from 0 to T naught by 2. A into e to the power j k omega naught t. This is equal to A upon minus j T naught k omega naught per minus j k omega naught t, putting the limits from 0 to T naught by 2. This is equal to minus A upon j k 2 pi. Omega naught is 2 pi by T naught. So when t is equal to T naught by 2, this is like saying it is e to the power minus j k pi. E to the power minus j k pi minus the lower limit 1. So I can write this as A upon j k 2 pi 1 minus e to the power minus j k pi. Now let us look at what values does this term e to the power j k pi take. Okay, let's look at it in the next slide. Now by Euler's relation, we know that e to the power minus j k pi is cos k pi minus j sin k pi. Now sin k pi will always be 0 irrespective of what is k, But cos k pi will be equal to 1 when k is even. That means k is equal to some 2m, and it's going to be minus 1 when k is odd. That means k is of the form 2m plus 1. That means I can write e to the power minus j k pi is equal to minus 1 to the power k. Okay. So for even case this is 1, and for odd case this is minus. So I'll go back to expression, and that was that ck came out to be a upon j k2 pi 1 minus e to the power minus j k pi, and I'm going to write this e to the power minus j k pi as minus 1 to the power k. This tells us that ck, and this is for k not equal to 0, this tells us that ck is equal to, whenever k is even, would be equal to, whenever k would be even, this term would be equal to 1, and this term would become 1 minus 1 equal to 0. So ck would come out to be 0 whenever k is even, meaning k is of the form k equal to 2m, but not equal to 0. And whenever k is odd, this term would come out to be 1 plus 1, 2. And 2 and 2 would get cancelled, and you would get a upon j k pi for an odd k, meaning of the form 2m plus 1. Therefore, I can say C0 is equal to a by 2, C of 2m, meaning all the even coefficients are also 0 from here, and all the odd coefficients are a upon j k pi, and k is odd, that means k is 2m plus 1. So a upon j 2m plus 1 pi. So now I can write xt as a by 2 plus a summation of these exponentials, a upon j 2m plus 1 pi into e to the power j k omega naught t, and k is also 2m plus 1. So xt is actually a by 2 plus a upon m varying from minus infinity to plus infinity. So a upon j pi, summation of m from minus infinity to plus infinity, 1 upon 2m plus 1 e to the power j 2m plus 1 omega naught t. This is the complex exponential Fourier series representation of this wave. How about the trigonometric representation, where a naught would be equal to c naught, which is a by 2, ak would be equal to, is twice the real component of ck, remember, but ck came out to be a purely imaginary number. The real part is 0. ak for even case is also 0, and ak for odd case is also 0. What was bk? Bk was minus twice the imaginary part of ck. Now ck for all the even case came out to be 0, right? So b of 2m, meaning all the bk's which are corresponding to even values of k, so of the form b2m, are also 0, because how about odd values of k, meaning b2m plus 1, that means bk for odd case, this is equal to, okay, let me just rewrite ck here to avoid any confusion. ck for all the odd values of k, means of the form 2m plus 1, was found to be a upon j 2m plus 1 pi. So if I want to bring j in the numerator, this actually becomes minus j a upon 2m plus 1 pi. It's equal to minus 2 into minus a upon 2m plus 1 pi. So basically 2a upon 2m plus 1 pi. How can I rewrite it? xt is equal to a by 2, means a naught, plus 2m 2a by pi is a constant, does not have any term of m, so I can keep it outside. 2a by pi summation 1 upon 2m plus 1, all the odd sine harmonics. Okay, because this term is for all the odd case, where m varies from 1 to infinity. This is from 0 to infinity. From 0 to infinity. So I can rewrite this as a by 2 plus 2a by pi. When m is equal to 0, 2m plus 1 is equal to 1. So this means sine omega naught t. For m equal to 1, this denominator is 3. So this means 1 by 3 sine 3 omega naught t plus 1 upon 5 sine 5 omega naught t, and so on. Since xt was an odd function, it was kind of apparent already that it would have no cosine terms, because ak's would come out to be 0 and only bk's would feature. And what we actually found was, even among the bk coefficients, that means coefficients of sine waves, the coefficients of even harmonics of sine wave came out to be 0, and only the odd harmonic would feature in this waveform. So this is the trigonometric Fourier series representation of this wave. Now in your assignment, there is a question that you have to find Fourier series representation of a wave like this. Okay. Let us define this as some x1t. It is also a square wave, but its amplitude fluctuates between plus a and minus a. Now, in order to write the Fourier series representation of this wave, note that we can write this waveform as, we can write this as a summation of this square wave subtracted by a value a for all t. So basically it's like having a square wave, which we just saw in the previous example. Instead of amplitude a, its amplitude is 2a, and this is subtracted by a, means it is clamped down by an amount of a. This is what would be equal to this waveform. That means I could say that x1t, this waveform, is actually twice xt. If I define the waveform in the previous example as xt, I can say that this waveform is equal to 2 into that xt minus a. I have already written the Fourier series representation of xt. So I could write xt as a by 2. This is what we found out in the previous example. So a by 2 plus 2a by pi sine omega naught t. So this is t naught, this is 0, this is t naught by 2. Period of the waveform is t naught. This is t naught. This is t naught by 2, and this is 0. This is minus t naught by 2. So it has the same period. Okay. Plus sine 3 omega naught t 1 upon 3 plus 1 upon 5 sine 5 omega naught t, and so on. This is what is xt minus a. So this would become 2a by 2. So a, and that a and this a would get cancelled, and all I would have in the output would be 4a by pi sine omega naught t plus 1 by 3 sine 3 omega naught t, and so on. This is what is x1t. Where this is what is x1t. Let us take a look at this demo of Fourier series representation in trigonometric form from Falstaff.com/Fourier. So what you would see here is the original xt on top, and in red you would see the Fourier series approximation up to say some nth term. Below here you would see the sine components, meaning the sine coefficients and the cosine coefficients. This xt, this current waveform, is chosen to be the square waveform. So this is an odd function and it would have no cosine terms. The average value of this wave is 0 over one period. Okay? So the DC term is 0. The average term is 0. Now I'm going to increase the number of terms and you'll see in red the summation of the trigonometric Fourier series representation up to that term. Okay. So this is k equal to 1. So for k equal to 1, cos term has come out to be 0, shown in yellow, and for k equal to 1, sin omega naught t, shown here as sin x, is shown in the yellow wave. And this is the waveform in red is the summation up to first term. Increase the number of terms. For k equal to 2, we already found that all the even sign coefficients came out to be 0. So for k equal to 2, b2 is 0. I increase the number of terms to 3. What is shown right now on the screen in yellow is the third harmonic of omega naught t. It's the third harmonic of omega naught, shown here as sin 3x. Okay, and the amplitude came out to be 0.4244. That means B3 came out to be 0.4244 for this particular frequency. Some frequency has been chosen. Okay, so what is that frequency is not important here. What is important here is that this is the third harmonic of that frequency. And shown in red is the summation up to third term. That means B1 sin x plus B2 sin 2x plus B3 sin 3x. B2 is 0. So this is basically B1 sin x plus B3 sin 3x, the waveform in red. As I increase the number of terms, you see that the red waveform, which is the summation up to that many number of terms, goes on becoming closer and closer to a square wave. And as expected, all the cosine terms are found to be 0, and when I point to these individual coefficients, you can see in yellow the waveforms corresponding to that harmonic. So this is the first harmonic, this is the third harmonic, this is the fifth harmonic, seventh harmonic, and so on. And all the even harmonics of sine are also 0. And shown in red is the summation of all these harmonics up to some term. If I go on increasing the number of terms in this slider, what we observe is that the summation becomes closer and closer. That means the ripples that you had go on compressing towards the discontinuity. Okay? But they do not completely disappear. We'll discuss that phenomenon shortly. Let us take another example of a sawtooth waveform. Let us look at another demo of Fourier series representation from desmos.com. My waveform of interest is shown in green, that is a sawtooth waveform. We can see that this is an odd function, therefore it would have only sine terms and no cos terms. Right? So the first sine term is shown in purple. The summation of first and second sine term is shown here. The summation up to first 3 sine terms is shown here. Summation up to first 4 sine terms is now shown in black. Now if I remove all these individual summations, and now in black you will see summation up to 8th term. Okay, so I'm increasing. This was up to 4, which is the same as this term. Okay, as I go on increasing the number of terms, we notice that the Fourier series summation becomes closer and closer to the original sawtooth waveform. This demo can show a summation up to 100 sine terms. Okay? Cos terms are 0 and sine terms are non-zero, and for this sawtooth waveform we actually find that the coefficient of sine wave would come out to be 1 upon n or 1 upon k. Here again, what you notice is as the number of terms is increasing, the waveform is tending towards the original sawtooth waveform, but an interesting thing may be noted near the discontinuity. So what you observe is, I'll zoom in into this discontinuity, and what you notice is that as I'm increasing the number of terms, the ripples go on compressing towards the discontinuity. That means this point x equal to 0 is the point of discontinuity. The ripples continue to compress towards this discontinuity. but there is no significant change in the amplitude of the ripples. Let us now discuss this phenomenon. So in 1898, American mathematician Albert Michelson, he developed a harmonic analyzer that could compute the Fourier coefficients up to k equal to 80. So it could compute ak up to k equal to 80. Okay. He used this harmonic analyzer to study the Fourier series representation of different waves. So following Dirichlet's condition, for all other smooth waves, the Fourier series representation exactly converged to the original signal as he increased the number of terms. But when he used this same equipment for a square wave, his results were kind of different. His observations were what we just saw in this demo. Okay. So he thought that probably his device has some error, and he wrote to Josiah Gibbs, another very famous mathematician of his time, who analyzed Michelson's findings and then published the results in 1899. So if you have some xt and you find its Fourier series coefficients, and let us define xnt as the summation or the Fourier approximation in terms of complex exponentials up to nth harmonic. Okay, so xnt is the Fourier summation up to nth harmonic, capital N. Now a square wave satisfies Dirichlet's condition. Therefore, at all time t which lies in the continuous part of the wave, the Fourier series representation would converge to the actual value of the signal, and at points of discontinuities, the Fourier series would converge to the average value of that discontinuity. That means the average of value on either side of the discontinuity. Shown here are those xnt's, that means summation up to nth harmonic. Right now this is for n equal to 1, that means summation up to first harmonic, that means an average value of half plus the first harmonic cos omega naught t. We are taking the example of the even square wave, which we considered in the very first example in this lecture. So this is for n equal to 1, and this approximation is superimposed on the original square wave shown in the background. Okay. So this is for n equal to 1, this is up to n equal to 3, this is up to 7th harmonic, 19th harmonic, 79th harmonic. Gibbs validated Michelson's findings, and he found that the partial sum in the vicinity of discontinuities actually exhibits ripples. The peak of these ripples does not decrease as n is increased. In fact, he observed that there is almost a 9% overshoot at these points of discontinuities. Let us consider some convergence at some point, say t1. If this time t1 is in the continuous portion of the waveform, then at point t1 the partial sum will converge to the correct value. Okay. However, at discontinuity, so here as per Dirichlet's conditions, the partial sum would converge to the average of value at just before t1 and just after t1. So let this be t1 minus and t1 plus. So it should converge to the average of these values. Gibbs found that as the number of harmonics in the partial sum is increased, the ripples in the partial sum become compressed towards the discontinuity as observed here. But for any value of capital N, that means for any value of number of harmonics, the peak amplitude of the ripples remain the same, and this behavior is called the Gibbs phenomenon. And this is typically observed in signals which have jump discontinuity. As stated before, for any fixed value of t, say t equal to t1, the partial sums will converge to the correct value, and at the discontinuity, the partial sum will converge to 1/2 of the sum of values of the signal on either side of the discontinuity. However, the closer t1 is chosen to point of discontinuity, the larger must be the number of harmonics in order to reduce the error below a specific amount. Thus, as capital N increases, the ripples in the partial sum become compressed towards the discontinuity, but for any finite value of capital N, the peak amplitude of the ripples remains the same. This behavior has come to be known as the Gibbs phenomenon. The implication of this phenomenon is that the truncated Fourier series approximation of a discontinuous signal, discontinuous meaning having some discontinuity, like a square waveform or a sawtooth waveform which has a jump discontinuity. If you find the truncated Fourier series approximation, that means approximation up to only some n, capital N terms. This approximation will, in general, exhibit high frequency ripples and overshoots near the points of discontinuities, and if such an approximation is used in practice, a large enough value of capital N should be chosen so as to guarantee that the total energy in these ripples is insignificant. In the limit, of course, we know that the energy of the approximation error vanishes and that the Fourier series representation of a discontinuous signal such as the square wave or a sawtooth wave actually converges because it follows Dirichlet's conditions.